All right, I'm back, still on page 271, kind of on the third problem, I guess. And let's see what we can do. So we want to find the limit as x approaches 2 of x squared minus x plus 5 all over x minus 2. You can see right away the denominator is going to be 0, right? But is the numerator? So let's see. We're going to get 4 minus 2 is 2. So we actually get 7 over 0, not indeterminate. So, woo. Not indeterminate. I feel like this is the wrong size. No, it's same size. Indeterminate. It's not indeterminate because it is not 0 over 0. It is not infinity over infinity. So kind of you could just say the limit does not exist because the limit doesn't exist. But I'm never happy with that. I always want to know, like, why doesn't the limit exist? So let's look a little deeper, right? So the answer to this is does not exist. So let's say the limit as x approaches 2 of x squared minus x plus 5 over x minus 2 does not exist. But why doesn't it exist? So what I'm going to do is I'm not going to look at the graph of this thing because I don't honestly really know what the graph of this thing looks like. Does the numerator have any zeros? So the discriminant, let's see, is b squared minus 4ac, right? So b squared minus 4ac. So b is 1, so it'd be 1 minus 4 times 5 minus 20, negative 19, less than 0, no real zeros. Okay, which means that the numerator is always positive in this case, right? Because of the plus 5. So the numerator is always positive. So all I really need to do is I need to look at what happens at 2, right? So what I'm testing here is I'm essentially testing x squared minus x plus 5 over x minus 2. But I know the numerator is always positive, so it doesn't really matter to me. The numerator doesn't really matter. So negative 1 billion minus 2 is negative, so we're going to get negative here. And then 1 billion would be positive here. Okay, so we know that x equals 2 is a vertical asymptote because it's 0, the denominator that doesn't cancel out. So it's a vertical asymptote. So if I kind of take this, I don't like to do this all that often because it kind of like messes up your number line, but like for the purposes of learning this, let's do it. So I know that perfect vertical line kind of went, you know, whatever. This function, if I were to graph it, is going to look like, so if I go to infinity, I actually get y equals x. Well, it doesn't really matter. Right around 2, it's going to go like this, and then it's going to go like this. So I can use that information to figure out the limit as x approaches 2 from the left and the limit as x approaches 2 from the right. So let me do that. The limit as x approaches 2 from the left of x squared minus x plus 5. Seem to have changed color here, which is fine. So 2 from the left goes to negative infinity. What? Negative infinity. The limit as x approaches 2 from the right of x squared. So like basically just don't settle, right? Like sometimes a limit will be really challenging. You'll know it doesn't exist and you just don't really want to figure out why. If you can figure out why, especially when you're first starting out, do it because it's going to pay dividends, you know, for really like years, infinity. So this is why the limit doesn't exist because we got negative infinity one direction, we got infinity the other direction. There's no way that limit exists. We already knew the limit didn't exist, but we wanted to know why. We wanted to dig deeper. All right, let's take a look at this problem. So maybe I'll stay on this color. We have the limit as h approaches 0. So if you think back to what I said at the beginning of the last video, I guess, h approaching 0 tells you that h is the variable, which means that in this problem, a is not really a variable. It's just like another constant, like pi is a constant, e is a constant. For this problem, a is a constant. We don't know what a is, but it turns out that it doesn't really matter. It's just a constant that isn't going to change. All right, so limit as h approaches 0. Quantity a plus h squared minus a squared all over h. Step 1, try to directly substitute and see what happens. So I'm going to do that. But you can see that if h is equal to 0 in the numerator, you get a squared minus a squared, so you get 0. And if h is equal to 0, then h is 0. All right, so we're allowed to do stuff. So it's indeterminate. You can do your algebra stuff. You can do whatever you know, all the little tricks that you're picking up along the way. I'm going to expand the numerator. I could view it as a difference of squares. It just doesn't save you any time. But it could be like a plus a plus h minus a, whatever. You could do that. I instead am going to do it kind of like the long way because I think that overall, that's how you're more likely to do it. A squared 2ah plus h squared minus a squared all over h. Okay, so I happen to know something about this particular type of limit, which is a really common type of limit. At that stage, when you get 0 over 0 to begin with, then you expand everything. If everything in the numerator that doesn't have an h doesn't cancel, so in this case, a squared, there's no h, minus a squared, there's no h. If everything like that, everything that doesn't have an h doesn't cancel, you did something wrong, and go back and find it, because it's always going to cancel. So here, limit as h approach. And the reason I know that is I've just done like hundreds and hundreds of these, probably thousands and thousands, really. So 2ah plus h squared over h. Look at this, we can cancel an h from like everything. Limit as h approaches 0. But as long as I'm writing h's anywhere, I have to keep writing the limit. So that's what I'm going to keep doing. So I get 2a plus h. And then if h goes to 0, I get 2a. So this limit is equal to 2a. This limit is a bigger deal than maybe you initially are realizing, though. Let's go into it in detail here. All right, so I look at this limit and I recognized it. I recognized it in particular because it's the limit as h approaches 0, which is like the most famous type of limit. What I'm seeing when I look at this is I'm seeing that there's a function, and that function is x squared. And we have 2 points. And what we're doing is finding the slope between them. Our 2 points are a comma a squared, and also a plus h, whoops, comma a plus h squared. Okay, so it's like a f of a and a plus h f of a plus h. So we could actually have written it that way. We could have written this limit as the limit as h approaches 0 of the slope between these 2 points. So I'm going to say it's f of a plus h minus f of a all over a plus h minus a. Okay, and then this would simplify down into the limit as h approaches 0 of f of a plus h minus f of a over h. So that's why the denominator is just h. It doesn't look as slope-ish because the a and the minus a just cancel right out. So what are we doing here? So think about it. We said we have this function. So we have this function, y equals x squared, which is like hard to draw. Let's pretend that's perfectly symmetric. And then we have a point. So I'm going to change colors. We have a point that's at, let's say that this is a. So then this height will be f of a. And then we have another point that's at, what other colors do I have access to here? Let's say this. We have this point that's at a plus h, which means this height will be f of a plus h. Okay, and what we've done is we found the slope of the line going through those. There's our line. So we found the slope, right? Which would be f of a plus h minus f of a all over a plus h minus a. So f of a plus h minus f of a over h. That's the slope of this line. So I'm going to write that. F of a plus h minus f of a over h. But then what happens is we get really curious, like what's going to happen if h approaches 0? If h approaches 0, though, that just means that this point here moves closer and closer to that point. And then ultimately, you'll get to exactly when h is 0. And when h is exactly 0, this little secant line, which is what we've been dealing with, right? A secant line is a line that goes through 2 points, becomes a tangent line. And this would be our tangent line. And the slope of this, we found, because we took the limit as h approaches 0, is 2a. No matter what a is, it's just going to be 2a. So if f of x, there's a lot going on here. If f of x is x squared, then the slope of that curve at x equals a is just 2 times whatever a is. So if a is -4, so -4 would be maybe here, right? So if a is -4, then we go up here, and we find the slope of the line tangent to this at this point. That slope will be -8. And we said in an earlier set of notes that there's actually a special notation for that, and it is f prime of -4 is -8, or dy dx is -8. These are all different notations for the same thing. This is a huge idea. This is one of the biggest ideas in all of calculus. It's like this idea and some other idea are like the 2 biggest ideas that you will encounter. But I think we're done with this problem. The answer to this problem was 2a. We just wanted to know, like, what are we even doing? And so I think we are pretty good with this, and I will be back in more videos to do more of the notes. So I will see you then.